Hey guys, welcome to yet another video on dynamic programming. You're watching Developedia, where I teach you not so easy programming concepts lucidly with visual clear representation. My name is Amatya, and in this video we're going to talk about the 0-1 knapsack problem. So let's take a look at the problem statement first. So there is a thief. He has got a knapsack with him, and he has went to a house to steal something. So in that house there are n items, and each item has some value and some weights associated with it. And the knapsack that the thief is carrying has a maximum capacity of 25. So what it means is that he cannot carry anything more than a weight of 25 in his knapsack. If he does, it gets broken. So what happens is that he has to make the maximum profit, and the way he can do that is by stealing the most valuable items he can steal from that house. And he has also to keep in mind that he cannot exceed the constraint of exceeding the capacity. So in this given situation, the task is to help this thief how he can maximize the value stolen. Feel free to pause the video in here, and then I'm going to give you the solution. Alright, let's take a look at the solution. So let's first start by trying to figuring out the problem and the subproblem. So the problem is clearly to finding the maximum value that can be stolen for n items and a given capacity of the knapsack. So in the given problem we can see there are two variables. One is n and the other is capacity. So therefore we can write a function mathematically, and we can say it to be knapsack with parameters passed as n and capacity. Now the subproblem we designed in such a way that we can form the problem from the subproblems using a recursive relation. Now the way we are doing this in here is that, just think about it. If the thief has in this index, let's say in this case n is 7, so this is 0 based indexing, so that's why this is range from 0 through 6. So if the thief is here and he has to decide whether or not he will pick up this item with a value of 3. Now if he picks this item up, then in that case he's going to have to live up with the rest of the items, and the weight of the knapsack that he has remaining, the remaining capacity that he can take the weights of the items off, is going to be capacity minus weight of 6. The reason is he has already taken that item, so therefore the capacity gets decremented by that amount. So therefore if he picks an item, in the subproblem the capacity is going to be decremented by the weight of that item, and otherwise if he skips the item instead, in that case capacity won't be updated, but just the index of the item that he is considering in that particular state is getting decremented. Now the way we can write the recursion for this is, we can write as knapsack of n capacity is equal to knapsack of n minus 1 and capacity. What he means is that when he skips the item, in that case we are just ignoring that item, and the capacity is remaining the same for the rest of the items. That is, if he skips the 6th item, basically this is the 7th item, if he skips this one, he has to live up with the rest of the 6 items and capacity being intact. But instead if he decides to take this particular item, In that case, what he gets as reward is basically value of n minus 1. Basically this 3 is getting added to his value. But what is the penalty in this case? Is that the weight he can take, the capacity he has remaining, is getting decremented by weight of 6, which is 1. So capacity is getting decremented by 1. So this is the recursion. Now what we need to do is that we need to maximize this part, this knapsack of n capacity, in such a way that the capacity is not exceeded and the value that the thief can get is maximized. Now let's take a look at the code. Alright, so similar to the previous video, I have the C++ and the Python code side by side so that you can follow whatever you feel comfortable in. In here we are assigning two matrices, basically arrays, values and weights. So these are basically the value and weight arrays we had right in here. Alright. Now in this recursion, first we write the base case. So what if the number of elements is 0? So if the number of elements is 0, in that case what happens is that he cannot make any profit, because if there is nothing to steal, where is going to make the profit from? So therefore in that case we return 0. Or if the capacity remaining is 0, what he means is that even if he has something on his plate but he does not have the capacity to take the same thing on his knapsack, in that case he cannot take that, and for that his profit or the value he can get is going to be 0. So this is the explanation for the base case. Now let's take a look at the recursive step. So what happens if the weight of an item, the nth item that he is considering, happens to be greater than the capacity that he can take? In that case he definitely cannot take that and he has to skip that item, because if he puts something greater than his capacity in his knapsack, the knapsack is going to break. So what he has to do is that in that case he has to skip it. So we skip, then return knapsack of n minus 1 and capacity as same as the previous capacity. Now otherwise, if the weight is basically less than or equal to the capacity, then in that case he has to make a choice whether or not he should consider that item. So if he skips the item, the profit he gets out of that is basically knapsack of n minus 1 and capacity, similar to the previous one. But if he happens to pick that item instead of skipping, in that case the reward he is getting is value of n minus 1, and the penalty he is getting in terms of capacity, which is negative of weight of n minus 1, because that is getting decremented. And we decrement this item number by 1. Now please don't get confused with this n minus 1 and this n minus 1. This n minus 1 is basically for the item we are considering right now, and this n minus 1 is because of the 0 based indexing. So if I had used 1 based indexing, I would have put here n instead of n minus 1. Same thing will be here. But as we are not considering that, we are considering 0 based indexing, so that's why we are writing this as n minus 1. So basically what we are doing in the driver code is that basically we are assigning the n, the number of items, we are fixing the capacity, and we are printing out the knapsack. That's it. Similar thing in the Python. Now let's try running this one. $121. So let's see if it really is 121, if this is at all a correct answer. So what can happen in this case is that let's say if we are taking this 90, the value 90, and we have the total capacity of 25. So let's write it down in here in comments. Value, and let's say we have the capacity. So let's say we have capacity 25, and let's say we are taking this value, which is the 10. So therefore we are getting 90, and the capacity is getting decremented by 10, so it's becoming 15. Then let's take this one, 20 and 5. Let's take this one. If we are taking that one, it is being so 90 plus 20, so this is 110, and the capacity is getting decremented by 5, which is 10. Now of 10 capacity, what is remaining? So this is done, this is done. Alright, we can take this one, 851. So it becomes 118, and this remaining is 5, and then these three are done. Then capacity 5, we cannot take this one, nor this one. We can only take this one. So let's take this 3 1. So would be 121, and the capacity remaining remains 4. And in this capacity, he is not taking anything from here. So value is indeed 121. This is the answer. Yeah, the program execution is correct. So keep in mind that it might happen that the knapsack that he is taking home back might not be full. It means that it's not important to fill the knapsack with its maximum capacity, but what is important is to maximize the value we can get out of it. So that's why in this case, as you can see, that the remaining weight or the remaining capacity that he has in his knapsack left at the end of the program execution is basically 4. So I mean, he is not actually filling the knapsack, but still he is taking the maximum value. So maximum weight does not always correspond to maximum value, and in this problem you have to keep in mind that you have to maximize the value, not the weight. It is not important to fill the knapsack. It is important to maximize the value. Let's try the Python one. Alright, I think Python will work. Yeah, 121. It worked fine. Alright, now let's talk about the time complexity. So as you can see in this, in each step we are making two decisions. Whether we skip this item or we take this item. If we skip this item, we are getting the knapsack of n-1 and capacity, this one. We are coming to this state. And if we are taking the item, we are coming to this state of the DP. Capacity minus of weight and the n-1 being same in the both cases. Now what happens is that, as we had discussed in the previous video of the Fibonacci one, you had seen that whenever we are having this bifurcation kind of thing, and this goes on and on until we hit the base case, as we have in this case, if we are using just a recursion without any memoization, in that case the time complexity becomes 2 raised to the power n, 2 to the power n. So can we improve it? Yes, we can definitely improve it, and we have to use memoization. Now please feel free to pause the video right now and try to think about how you can memorize this solution, and once you're ready, resume the video from here. Alright, so the idea of memoization is you have to memorize whatever is being recomputed. And that's how you can actually avoid recalculation of the same thing and thereby improving the time complexity. If you take a look at this tree, what you are essentially doing is that you are making the bifurcation at each step and you are picking up a decision whether you have to skip it or you have to take it. In that case, you are basically recalculating some steps over and over again, and that's why you are getting the exponential time complexity. Now, to reduce that, if you can memoize on n comma capacity, or that is the DP state, in that case, if you can do that, you can basically improve your solution, and that's how you can memoize. Now let's take a look at the memoized code as well. Alright, so basically the code is exactly the same as the previous one, the recursive one. The only difference is that this is memoized, and the way we are doing this is that we are declaring a map named as memo in case of C++ and a dictionary as memo in Python, and then the base case is exactly the same. And instead of going into the recursion first, what we are doing is that we are checking if it has already been computed before, and if it has, then in that case it should definitely be in the memo, and if it is, instead of recalculating, we just return it from the memo. It's just kind of caching. If it is present in the cache, we don't reload it into the primary memory. That's why cache is used. So memo is similar to that. So same thing in Python, we check if this tuple n capacity present in memo. If it is, we return this. It's pretty easy. And other than that, what we do is that in the recursive steps, instead of returning it directly, we just store in memo first and then we return it. And the reason we store in memo is because if we need it in future as well, then in that case that value will be present in the memo, and so that we don't have to recompute it again. Now, what is the data type of the memo? In case of Python, it's pretty easy, you don't have to write anything. But in case of C++, if you can see here, you will be seeing that the input parameters of the map is going to be two integers, that is the n and the capacity. So what we are doing is that we are creating a pair of int, and this will basically represent the DP state, which is n and capacity. And the output data type of the map is going to be integer, which is the maximum value that the thief can get on that particular DP state. So that's how we do it, and other than that, everything is exactly the same as the previous one. Cool. 121. Good. Alright, now let's do the complexity analysis of the DP solution. Now the complexity of a DP solution is always complexity of each state times the number of states we have in the DP. Now if you look at the code, what you can see is that in here, in each state, basically in each execution of this knapsack method, can you see any for loop or while loop or anything that can give rise to a O of n complexity or something like that? You don't, right? Because what you are only seeing is that you are only having if else statements, and this is the O of one thing. It definitely goes into the recursion, I'm not denying that, but the complexity part of recursion is taken care of by the number of states possible. Just think about it. The maximum number of times that this knapsack of n capacity can be calculated, I'm not saying invoked, can be calculated, is basically the maximum number of combinations of n capacity is available. So what I mean by that is basically if you see that if n is 7 and capacity is let's say 25, then in that case the maximum number of times the knapsack of n comma capacity will be calculated is definitely going to be n times capacity. You think in terms of combinatorics, you'll get to understand. So therefore what we do is that we multiply the number of states possible in the DP times the complexity of execution of each step. Because let's say there had been a for loop or a while loop something in here, then in that case it would have been O of n. But if it is present already and if it is coming in this part, if it is present in memo, what we are doing is that we are just returning from the memo. So anyway, if it is present in memo, it does not contribute to the time complexity because it is a O of 1 operation. But in case if it is not present in memo and we have to calculate it, it means it is coming inside this function for the first time. Only in that case we are taking into consideration. So therefore this part is what we need to focus on, and the complexity definitely is O of 1 in this part. So therefore the complexity of the overall thing is going to be the complexity of each state, which is O of 1, and the number of DP states possible. So how many values of n can be possible? Just think about it. 0, 1, 2, 3, 4 till n, right? So n values can be possible. How many different values of capacity can be possible? 0, 1, 2, 3, 4, 5 till capacity. You cannot have capacity or something in negative, because just think about it. You are decrementing n by 1 in each step, right? So n is a positive value, and once it reaches 0, it is your base case. You are returning something. So n cannot be negative. That's clear. Alright, now can capacity be negative? Capacity can only be negative when you subtract some weight which is greater than the capacity. But you are checking in here in each step, if weight is greater than capacity, you are not considering taking that item at all. You are skipping that item straight away. So it means the capacity also can never be negative, right? So the only possible values this n parameter can take is 0 through n, and the only possible values that the capacity parameter can take is basically from 0 through capacity. So the different combination of n capacity available in this particular DP state is going to be n times capacity. So that's why we are having the time complexity as n times capacity. Alright, so that's it for this video. That's all about the 0-1 knapsack problem. So there is basically another problem which is fractional knapsack problem, where you can actually fractionally take something. In that case what you can do is that you can just sort the values in decreasing order of value upon weight, the lowest weight and the maximum value items you will be taking, and will keep on taking in your knapsack until you exhaust the entire weight. So that is basically a greedy solution. I can discuss this in another video if you want. Just let me know in the comment section that if you want me to discuss the fractional knapsack as well. Like and share this video if you liked it, and you can do few things to be a part of the Developedia community. So what you can do is that first you can subscribe to Developedia YouTube channel. Secondly, I post all the codes in GitHub that you can find regularly, and I'm pretty active on GitHub. You can follow me on GitHub as well. There is a Facebook page for Developedia. You can like this page and follow, because I will be posting few updates, and if I have something to discuss with you guys, we can have a healthy conversation in here in the comment section as well, and that will be pretty interesting, I believe. So let's do it. Let's like and follow this as well. And also follow me on Instagram so that we can build a large community on Instagram, and that we can use for like sharing some opinions and posting some photos and whatever, and providing some updates that we have and whatever. be a part with us, and thanks for watching this video till the end. Catch you guys in the next one. Peace.